Hello guys, I apologize that I came a little late, like 2 minutes or so late, and I still people are coming. So first question is, of course, do you remember when the exam is due? Do you guys? Wednesday. And of course, guys, I see a few of your faces. If you can turn more cameras on, that will be amazing. Thank you, Alice. And of course, I myself forget when the exam is due. Do you want me to forget when this exam is due? Because I noticed that suddenly people are asking me questions. I mean, how to solve this, how to do that. I'm having a problem with this or that question. So very quickly, write down if you want me to forget when the exam is due, as I tend to forget dates. Is it due maybe this or next Wednesday? So if memory serves me, yeah, Jack, exactly. Usually it's 9 months, the due date is in 9 months, but since this is CUNY, it sometimes is 10 years. Good? All right, so I presume, guys, I think it's due not this Wednesday, but the Wednesday after this one, correct? Understood? So if you have or need the time to work on it, go ahead and work on it. I'm glad that you understood that I was getting the sniffles with the rage virus, and a little bit more people came to this class than they started coming, right? Or maybe it's raining and you do not have anything better to do. Regardless of the situation, let's get back to the lecture. And if you have the time, I don't care. Do I measure time? Right. So it's due on Wednesday. If you have to, it's due very late Wednesday night. If it's super important, submit it on Thursday, right? I would probably not start grading it before Friday if I will start grading it. Good. So do your best. Work on it. Think about it. If you have questions and would like to discuss, I know, Alan, you asked me something and we can talk about it after class. We can talk about some ideas if they help you. Good?
Arkady.
Yes.
So the due date is still the 14th of this week, right?
I don't remember dates. Apparently, it's in 1 week. I mean, people, I asked them, I don't remember, and apparently it's due on Wednesday that is after this week. So not this Wednesday, but the one after. Good? And if you cannot get it done on that Wednesday, you can work on Thursday. Fine, right? There's no particular time. Just make sure that once I disclose the results on that exam, and I will give you a warning, once I give you the results, we will discuss the exam. Good? That's it. When we discuss the exam, I will not accept anything after. So I'll try to keep discussing the exam later because the exam disgusts me.
All right, so next week, the 21st.
I don't know. I suppose next week on the 21st, if that's the Wednesday. Or if it's maybe 22nd, whatever, right? We are not in Germany.
Thank you.
Good. So let's talk about briefly, guys, what we did last time. Recall that there is such a thing known as random variable. Random variable. And this is something much simpler than it sounds. Trivially simple. Here is a sample space. And here is an induced sample space, a star. Good? And you have events, let's say 1, 2, 3, 4, 5, 6. And the induced sample space, so this X carries, let's say 1, 2, 3 to the input A, 4 and 5 to the input B, and 6 to the input C. Good. So what is that random variable doing? This is the random variable X. It is just in effect relabeling the outcomes 1, 2, 3. So those outcomes are labeled A, and A. The outcome B, B labels 4 as B and 5 as B. And the outcome C is labeling 6. You understand what's happening, guys? So a random variable is just relabeling, usually relabeling that corresponds to numbers. You assign numbers to individual outcomes of a sample space. Good? So you can either think of a random variable as a function that take elements or pebbles from one sample space and maps them onto another space. By the way, Sarah, you missed the fact that I forgot when the exam is due, and apparently it's due not this Wednesday, but the Wednesday after that, because that's what people told me it's due and I forgot. Understood? So yes, so you'll see what happened here, guys. And so what's the probability of event A occurring? It's now the same as 1, 2, or 3 occurring. And so you add up the probabilities. So basically, you can speak of the probability where X equal to A. And that simply is the probability that 1 occurs plus probability that 2 occurs plus probability that 3 occurs. Understood? So you can either think of it as inducing a sample space, or, which is equally important, to think of X as relabeling the outcomes of the sample space, giving some distinct outcomes in the sample space the same name possibly. You understand? And that's all that function is doing. A random variable, the reason it's called random is because the outcomes, the actual inputs, you see, so really what's happening here, it's really X of 1 equal to A. And 1 second, guys. So it's just a function, absolutely right, right? X of 1 is equal to A. X of 2 also equals to A, and so on. It's just a function. The function has to be, of course, onto. Why onto? Because you can just think of the individual outcomes in the sample space. Each individual outcome has to be assigned a new designation. You understand? I could map all of them to the same number. I can map individuals, some groups to one number, other individuals to another number. Usually you prefer to map it into numbers, even though it's not required. Understood, guys? So the idea of a random variable is as simple as it possibly could be. And then the next thing that we talked about is the expected value. And that we will learn to calculate in different ways, and it's a very, very crucial and amazing result, especially if you like to stereotype and offend people, right? So that's especially useful result, because then you can use mathematics to justify what you do. So here is the situation. So if you have a random variable X, which maps a sample space into some subset of real numbers, for instance, you can think of the results as payoffs, or let's say as individual outcomes of chance producing different payoffs. The expected value of X is defined to be the summation of all possible values that X can take. And this would be, let's say, X equal to the value XK multiplied by the probability of XK happening. You understand? So maybe I should write this simply as XK times the probability that X equals to XK. Now, why is that a good definition of an average? You understand what is the expected value supposed to do? It's supposed to tell you what will happen to you if you make a habit of doing something, right? In other words, don't do it once, twice, 3 times, but do it consistently and constantly. right? What will happen? Okay, so the simplest way to understand that is you play a game, and I will make the number of outcomes, number of payoffs finite, just because it's easier to picture this. Good. So the number of outcomes that can happen is x1, x2, all the way to xn. Everybody understands what I mean by that, guys, right? So if you throw a dice, if you throw a die, then you might have, let's say, 6 different payoffs. Maybe you get $1 if you roll number 1, and maybe you get $2 if you roll number 2. You understand? So there are just finitely many outcomes. What will happen on average as you roll those, as you roll the die, as you play this game? So you can imagine that the game of chance, it will produce. So if you played n games, then you might say nk of them produce payoff xk. You understand what I mean by that, guys? So you play a huge many games. N is a huge billions upon billions of games. How many, that depends on the particular random event you're studying. But if you play a huge number of games, the bigger the better. And then nk of them will produce payoff xk. So in other words, n1 is payoff n1, etc. Right? So what you have is n is the number of games, absolutely. N is the total number of games you played. So imagine you roll the dice 1 million times, right? And let's say 1 million over 6 of the times, maybe the outcome was 1. Good? Or 6 million over 6, let's make it a nice number. You threw the dice 6 million times, and 1 million of those times, the outcome was that the die showed up with 1 unit. Good? And maybe 1 million times it showed up with number 2, and on and on. And nk is just that, what I mean is that 1 million. It's the number of times where a particular outcome came to be. It's how many times that very specific payoff came to be, right? So just if you have an analogy, think, you know, that you get $1, so that x1. If the outcome is that the die is displaying 1, good, the die comes up 1, and 2 is the number of times the number 2 was displaced, and then you got $2. So then you can average by grouping the like. Remember that, guys? So what's the average? So obviously it's divided by n. What's the average you win per game? So it would be n1 multiplied by, or I will just write it this way. I would write x1 multiplied by n1 plus x2 multiplied by n2 plus xk multiplied by nk. Right, maybe I forgot how. Let's say we have m possible outcomes. Let's say like this, m possible outcomes. Good. Guys, so that you comprehend what's happening, tell me the numerator signifies what? In the simplest possible language. What I wrote here, the summation, it represents what for those games you played? James, you look like a character from some Star Wars. I don't know. I don't really know Star Wars well enough, but
I don't watch Star Wars either, so I don't know what you're talking about.
Okay, good. So none of us do.
Okay.
So payoff divided by outcome times what it, well, simpler. Alice and anybody else, if you could give me the simplest possible explanation of what's that sum. Yeah, sorry, not divided, but what's the sum? In very simple words. This sum represents what? You go to a casino and this sum represents what? No. What I just wrote, it's not the expected value. No. You played those games, right? So first of all, what's true about the summation? First of all, observe that n1 plus n2 plus nm must equal to n, the total number of games you played. You agree? You understand, guys? So what is that sum? Simplest thing possible. The sum represents, before I say it, please.
The total rounds.
Close. The total what? What you're going to pocket from the casino, my God. My goodness, right? You just added up, but you know what you did, guys? You earned $10 bills, $20 bills, $50 bills, and because you're organized, you group them into piles, right? You take a rubber band and you tie together all the 50s, and you tie together all the 20s and all the hundreds and all the units. You understand what you're doing here? You group together payoffs. And instead of counting, let's say 1 plus 50 plus 20 plus 1 plus 7, what do? You group the money by categories before you do that. Is that clear? So what you imagine is that the money that there are M different types of payoffs. So you group the payoffs into one pile, the same payoff into the same pile, and just count how much is in that pile. How many ones, how many fives, how many tens, how many 50s, how many hundreds. You understand? And then I tie them with a rubber band, and I can calculate my total winnings. Clear? For all the games. Now, how much did I win per game? I just take that and I divide by n. Are you with me, please? Now, what does it represent? I divided by n, it represents what? Well, and in particular, because those words, maybe you understand what they mean, but maybe you do not. Expected, what is that divided by n? Well, n is total games, but yes, average per game, it means how much, if each game brought you the same amount of money, how much would that be? Do you understand? It's an idea that you should be very comfortable with by now, right? It's like taking all the thing that you have and dividing it equally among everyone. So it's the amount of payoff each game brings if the game was to bring a constant payoff. Do you understand? Clear? So this is the average, and then look what happens, guys. N is huge. This can be written as x1 and 1 over n plus x2 and 2 over n plus xm and m over n. And then tell me, what is that? Yes, Rodney, and that is the probability. Do you see why? What is probability based on running frequency? How do we tell that something is, let's say, remember where we started. How do we know that a coin is fair? Experimentally, we just throw the coin many times, and the idea of it being fair is that if you saw it many times thrown, then you think that if it's fair, then there would not be preference for the coin to land on tails or heads. And so exactly the number of heads to total number of throws approaches 1/2. It's never exactly 1/2 necessarily, but it approaches 1/2 with less and less difference. Remember, we did simulations. It's very difficult concept because you can be confused. How many times do you throw it? If you throw it 1,000,000 times, technically that does, and you don't see a half, technically speaking, it doesn't mean the game isn't fair. The idea is in the limit, right? That nature, given enough opportunities to show its preference, it will show its exact preference. With enough repetitions, justice will triumph, right? That's at least what the idea means intuitively. And of course, you can try to use the axiomatic approach where the probability now becomes absolutely reasonable, right? And then the limit can be deduced from that probability. Okay, so the law of large numbers, which we will study later on. Good. So it's a weighted average, absolutely. So what is that approaching? This, as n goes to infinity, this should approach to probability of x1 occurring. So that's x1, probability x1, plus x2, probability x2, plus xm, probability xm. And that is expected value of x. I did it for a finite situation, but you can imagine the same result should hold for infinite situation. That's why we define it. That's why we define expected value by this formula. You understand, guys? Our intuition is probability begins with that intuition. Good. This I like the frequency approach, the sequential this thing, right? So I believe that this limit will converge, and if it converges, then I can read what the formula should be. Understood? In the axiomatic approach, you might think, I believe I know nature's preference, and then from that you can prove that the limit will converge. You understand? If I know nature's preference, then that's the law of large numbers, then the probability, the sequence will converge to that value, to the probability. But both of them are very difficult, because I mean, how should I know that I know what nature likes or what nature prefers, right? And if I do an experiment, well, maybe I didn't perform it long enough, or if I repeat the experiment, some other results will come. Good. So that's one of the difficulties of probability. All right, so then let's talk about this situation, guys, where we roughly left off. So we want to understand the properties of cumulative distribution. And one of those properties is that if I have a sequence of increasing events, that means increasing events, that one event is contained in another, then and their union is E, then I can calculate probability of E by taking the limit as n goes to infinity of the probability of the E sub n's. Understand? I can take any one of them and take the limit. Now that can be demonstrated as follows. So the E's are not disjoint. So I see the union is this. This is my representation of E1. This is my representation of E2 and of E3. And they go as concentric disks, bigger and bigger. Yes. Now I can use that union and make it a disjoint union. That's not hard to do, because I can say F1 is equal to E1. And then F2 is whatever is in E2, but not in E1. You see, so F2 is represented as this annulus. F3 is what's in E3, but not in E2. Clear? So now the F's produce exactly the same union, except now it's disjoint. Do you see that? And not only that, if I take the union up to some capital N, the union is still disjoint. Finite union is disjoint and equal, because I either just say E1 and E2 and E3, and thereby add many times the E1 and E2, or I can say E1 once, whatever else in E2, and then whatever else in E3 that's not in E2, and I just take the union of the F's. Clear? So that means that probability of E is the probability of the union of En, which is the probability of the infinite union of the Fn, and that's disjoint. And I can write it by axiom 3 as an infinite sum. Yes? Don't disappear, guys. So the summation, it's just the limit of partial sums by how we understand it from Calc 2. Good? And then this summation I can bring back into a union, because it's a disjoint summation. And remember, we proved as one of the theorems that disjoint summation, finite or infinite, can be brought back to the union. This is what we have. And look at what we have here. And this thing, as n goes to infinity, this union is the same as the corresponding union of the ENs. And this union of the ENs is just the biggest one, the last one. And we have proven our assertion. Do you see that? It's pretty simple. We have proven that you can just take the probability of one of those events and just take the limit. Alan, yes? You look unsatisfied with this proof. Or maybe you think, well, so what? Yes, we'll see why. I mean, it's important once we get to continuous distributions, I hope. All right, so here is the second lemma, is the reverse of that. If I see the probabilities are contained, so the events are contained one in the other, they are decreasing events, and E is the intersection of them, then similarly, the probability of E is the limit of one of those events. Good. So I don't need, so I can calculate the probability of the intersection by just taking the probability of one event and pushing the limit. So it's a sort of result on continuity of the probability function. And here is how we can do the proof, guys. We can convert it back to the situation we already know how to deal with. We know how to deal with unions. Good. Of increasing functions. So here is what we have. If I take E complement, that's the union of the En complements. And in that situation, if I take the complement, you can see that E1 complement is contained in E2 complement and so on. Do you see that? If the E's are contained, if E1 contains E2, E1 complement is contained in E2 complement. You agree? Because complement is like I throw it away, right? If I throw less away, then I have more remaining. Right, so E1 contains E2. That means if I throw E2, I might have not thrown all of E1. So it reverses the membership sign. So we have the situation here, and so the probability of E complement is the limit of the probability En complement, which is defined to be the limit as n goes to infinity 1 minus the probability of En. And this part is also defined as 1 minus probability of En. So we can just simplify and we see the same result. Probability of E is the limit as it goes to infinity of the probability of En. And this is what we can say relating to random variables. If X is a random variable, the cumulative distribution is capital F sub X. And that's defined to be the summation of all the probabilities where X is equal to B or less than B. And this is the result that we can observe. First result is that if A is less than B, then the cumulative distribution at A is less than or equal to the cumulative distribution at B, and that's obvious. You agree? Because here we have gathered fewer events potentially, and here we have more, right? X less than or equal to A is contained in X less than or equal to B. Another situation that we can get is that limit as B goes to infinity of the cumulative distribution will always go to 1. Now, how can we use that previous result for that? Look at it. We can define E sub n to be X less than or equal to n. X is assumed to be a real number, right? So what we have is E1 will be contained in E2. You agree? If X is less than or equal to 2, that will imply X it already contains all the situations in which X is less than or equal to 1. So this is an increasing sequence, and R is the union of those sets. So we know that the probability of getting a real number is 1. Because X is a random variable that's real valued. It's going to produce a real value. Good? When we do this thing, we're assuming that we're dealing with real valued random variables. And so that one will be the limit of those events, which is the limit the limit of n, which of course implies if it's true for integers, it will be true for any other value, because that value b is between or it's bigger than some integer. Good. So its behavior at an integer will be the same as its behavior at any other value that goes to infinity. I hope you see that. Some of you squint, so maybe you do not. Sufficiently clear? It's a bit technical, and I hope to move through it fast. What split up, Sarah?
Like you're saying f sub 1. What is the cumulative distribution?
I'm saying, I don't say f sub 1.
Or it's, sorry.
This is just an index to say it's the cumulative distribution for the random variable x. Yes? Right, so this is just a general property. General property is that the cumulative distribution is an increasing function. It's over R, right? So just x is a random variable that produces real values. The bigger the number, the bigger is the cumulative distribution added. So it's an increasing function. It will increase to 1. In the limit, as you go to infinity, it will go to 1. Maybe it will get to 1 and stay there, but it will grow to 1. The cumulative distribution always grows to 1. Good.
So, sorry, in this case, A and B are both numbers of trials, and so
no, it has nothing to do with any trials. A and B are just particular values that the random variable generates.
Okay, like
because here is what our random variables. I should make it clearer, guys. So the random variables of interest for which we calculate expected value, they can be for our purposes they will be taking real numbers, right? So we are going to say x is some function that maps s into real numbers. Maybe it's discrete, maybe not. Maybe it's onto R, maybe not. Right, but its outputs are numbers because we think of the random variable as generating payoffs. Maybe how much we win. If it's negative, we're losing money. If it's positive, we gain money. Good, and so the random variable is always going to produce, because any outcome in S, that means a little s, right? Not the big. That just means. Let's do this. If little s belongs to S, then x of s will be an element of R, will be a real number. Yes? So then I define the cumulative distribution for this random variable as, let's say, for A, this is just any real number, right? So if A is in R, I define f sub x of A to be the probability that x is less than or equal to A. In other words, this means the probability that I will get either A or something smaller in my experiment. Right? And so what properties do we observe about this function? So one property we observe is that the function is increasing. So if it's this. It's a non-decreasing function. We can say just increasing. You understand? Because the bigger the value you set, the more likely you are to get x in that you see, because you're giving x a much bigger range, and then that's more likely that the outcome will be what you like, right? So it's increasing. And second part that I'm claiming is that limit as b goes to infinity of x of the distribution is 1. It will grow to 1, right? As you set the bounds farther and farther, if you say, well, what's the probability x is less than 10 billion trillion, right? So that's very likely, it's almost certain. For most random variables that you encounter, it's essentially 1. So as you go farther and farther to the right, the probability that x is less than those values, the value b that you selected, then that border is going to increase. And it's going to increase to 1. That's what I'm saying. Make sense?
Thank you.
Sure. So similarly, if I move all the way to the left to minus infinity, what's the probability that my random variable is going to be less than that extreme negative number? It's going to approach 0. And this is a proof because we can set En to be x less than or equal to minus n, and we can see that E1 is containing E2. In other words, why is that true? It's that of course, if it's less than -1, that is already implied if it's less than -2, right? So you see, all possibilities where x is less than -2 are already contained in the possibility that x is less than -1, and so on. So that's a decreasing sequence, and their intersection of such events is going to be empty, because x is a real number. It's supposed to give you a real number as you go and select negative numbers with bigger magnitudes. Right, you're just moving like this. Right, so this is 0, this is -1, this is -2. You're moving in that direction, and you're saying x has to be in this region. And as you go with n to infinity, you are going to eliminate. The intersection is the empty set. There's no real number that belongs to all En. Do you see that? Because every real number is bigger than some negative. Okay, so that means that the intersection is empty. So 0 is the probability of the empty set, which is, according to one of the properties above, it's the limit as n goes to infinity of Pen, which is this limit. Right? All probability questions about x can be answered in terms of cumulative distribution function. So the CDF is cumulative distribution function. So for example, suppose I want to calculate the probability that x is bigger than a but less than or equal to b. How am I going to do that? So you see, suppose I know the cumulative distribution function. How am I going to use that to calculate this interval? So I can see that this is the same as the probability of x being less than b. Remove from that the event where x is less than or equal to a. Do you see this? What bothers me, of course, guys, that it's not clear from this discussion where I'm just introducing it because it was introduced in books there. You will see when you go into chapter 5, you will see that when we talk about continuous random variables, that this cumulative distribution function is important. For discrete random variables, I have myself a hard time to see the use of it. Understand? But once you have integrals, the cumulative distribution function is going to be an antiderivative. Okay, and you will see that this relates to the fundamental theorem of calculus. I see a few people, guys. What happened? I suddenly hear one person disappeared, another person disappeared. Turned off the cameras. So, do you see, guys, that this probability of x being between a and b is the probability that x is less than or equal to b minus the x being less than or equal to a. This is an intersection. It's x less than or equal to b intersect x less than or equal to a complement. Do you see this statement, guys, logically? This is an event, right? If x is between a and b, it means that it happened that x was less than b, and it also happened that x is not less than a or equal to it. So how can I calculate this intersection? Well, this is a, and so you can see you can write this as the probability that x is less than b minus the probability that x is less than b and x is less than a, right? You see that? Because it's like probability of b intersect a complement, and probability of b intersect a complement is the same as probability b minus probability ab. Yeah? Yes, where are you lost? Let's do it on a separate board. Here, we are trying to understand how to evaluate this type of probability. Now, in terms of fx. Okay, so in other words, suppose we have this cumulative distribution function. We have this function that can tell me what's the probability of being less than a number, but not this particular situation. You follow what I'm saying, guys? I'm sorry for this particular lecture. I'm sorry, it's kind of a bit dry and a bit cut out from where it should be, but bear with me. You see, guys, we have this, it's like you have a calculator, right? And let's say you have multiplication, division, you have the square root, it's like an old calculator, but you don't have the cube root. How do you calculate cube root? This is the type of question we're dealing with. So we want to calculate this probability, but we only can calculate probability of x being less than something. How do I use that information to figure the desired probability? Clear? Yes. So how do I do that? So I look at the situation and I'm trying to write it in terms of x less than or equal to something. This is where I'm trying to get. Everybody understands why? Because this is the only thing my machine is able to calculate. So I'm trying to get the statements in terms of x less than or equal to something. So how do I do that? So if x is bigger than a and less than b, the only possibility for that is that we have that x is less than or equal to b and x not less than or equal to a. You see that? If x is bigger than a, it's not true. That's why I have the complement that x is less than or equal to a. And then how do I calculate this thing? How do I break it apart? So that's the same as the probability that x is less than or equal to b minus the probability that x is less than or equal to b intersect x less than or equal to a. You follow? Guys, do you see how I get from this statement to the one below it? Confirm if you do, please, or if you have some questions, let me know. Okay, Erin says yes, that's good. I don't see the proof in the video, but she says yes. Roadra says yes. Jennifer says yes. And there are the others no. Guys, here is sample space. Here is B. Here is A, right? So what is in B and not in A is this set. This set is B and not A. And what is that probability? It's the probability of B minus the probability of the intersection. You agree? Because I take the full B and remove what's common to A and B, and that will give me B and not A. Clear?
Clear.
And it says that my internet connection is not stable. Is it not stable? Stable, yes? No?
Seems fine.
Hopefully soon I'll have better internet. All right. So that's what we achieved, you see? So we achieved x less than b minus x less than b and x less than a. But a is smaller than b. The intersection is simply x less than a. And so we get probability of x less than b minus probability x less than a. It's f, capital F at b minus capital F at a. If you remember the fundamental theorem of calculus, that's very similar to what you did when you integrated. Remember, the antiderivative was capital, so it should remind you, and you will see later why. You see, so it should remind you of this statement. Yeah? Not coincidence. All right, so suppose, for instance, we want to figure out how to calculate the probability that x is less than b. Notice there is not less than or equal. Right, I just need less than b. So what can I do? Well, I can creep towards b. So what I can do is I can take events of the form x less than b minus 1 over n, and that's event e sub n, so to speak, right? And we know that as I increase the n, I'm growing, right? The event is bigger. X less than b minus or equal to b minus 1 over n will grow as I make n larger. Do you agree? Because I subtract less and less. I'm making sense, guys? I'm not sure. Right? So b minus 1, b minus 1/2, b minus 1/3, I'm growing, right? X is allowed to be, it's allowed to grow. It has a bigger ceiling to grow to. Got it. Very good. So because of this limiting property of probability, that if the events are increasing, the limit of the increasing events will be the desired probability. So this is just the limit as n goes to infinity of the cumulative distribution of b minus 1 over n. Good? Here is an exercise for you guys. Do your best to figure it out. I'll help you. Ready? Here is a cumulative distribution for some random variable x. So here I'm just creating a situation where you don't know the probability, but you know the cumulative distribution. Now I want you to calculate probability that x is less than 2. Go ahead. You have 3 minutes. Can you see it? And then afterwards, probability that x is less than something else. Well, let's begin here. Probability x less than 2. You're not jumping with the answer, guys. So my explanation was not good. Yes? All right, let's try. We want x to be less than 2. Yeah. 2/3, correct, Jack. So why is it 2/3, guys? Look what happens here, right? So I can calculate the limit. So this is the limit as n goes to infinity of the probability where x is less than or equal to 2 minus 1 over n, which means where do we locate ourselves? We locate ourselves, this is the cumulative distribution. We locate ourselves between 1 and 2. And between 1 and 2, the cumulative distribution always gives us 2/3. And that is our answer. Clear? All you have to understand, guys, is that probability cumulative distribution is increasing, and it's continuous if you move from below. You understand? There is continuity. If you take a limit from below, it will grow towards it. Good? So the answer is 2/3. Can you calculate probability that x equals 1, please? That x equals 1. Here, I'll write it over here so you can stare at the equation. I want probability where x equals 1, please. Okay, Sarah says it's 2/3. Jack says 1/6. Remember, guys, this thing is the same as probability that capital X less than or equal to little x. Don't forget what this means. I want probability that x equals to 1. Okay, Jack and Jennifer, you agree? All right, 1/6 again. So a few people agree, but not a lot respond still. I see 4 people. And some even disappeared. Okay. Here is how we can do it, guys. Look at the situation. X equal to 1. It's the probability where x is less than or equal to 1 minus the probability that x is less than 1. Do you agree? If I want 1, I mean, I just take those are this is the elimination, right? It's x less than 1. You can even do it slower if you prefer. Let's do it slower so you see how I make all the moves. So what is that? This is the probability that x is less than or equal to 1 intersected with the complement that x is less than 1. You agree? It's true that x is less than or equal to 1, but it's not true that x is less than 1. logic. Yeah. So what is that? This is the probability that x is less than or equal to 1 minus the probability that x is less than or equal to 1 intersect with x less than 1. But x less than 1 implies that x is less than or equal to 1. So this is the smaller event. Yes? So that means that the result is simply probability where x is less than or equal to 1 minus the probability that x is less than 1. Good, you wrote it down, guys. I'm keeping this board, so I want to clear it. So what does it mean? And this probability here can be calculated as limit where n goes to infinity, the probability that x is less than or equal to 1 minus 1 over n. Yeah, I can approach from below. So what do? I see probability that x is less than or equal to 1. It's here. It's 2/3. At 1, it's 2/3, right? So the answer is 2/3 minus the probability that x is less than 1. If x is less than 1, then I use this equation, right? So what is x? X is approaching 1 from the left, so it's approaching 1/2. So it's 2/3 minus 1/2. Yes, Jack, go ahead.
Do we always assume that n approaches infinity?
Well, I mean, but we are making it do that because our goal is to calculate this particular probability, and we can use limits. That's all we're doing. Yes.
Okay.
So just what is my goal? My goal is to write the particular problem in terms of operations where I can apply this function, because I'm only able to calculate this function. Yes, so then I have to, you see, guys, what it worries me that you might have not understood the increasing or decreasing property of probability. But if you do, then it's obvious that you can do this process. You understand? Why do I take that limit? It's a limit of increasing sets. It's E1 is, in this case, x less than or equal to 1 minus 1. E2 is x less than or equal to 1 minus 1/2, and so on. You understand? So I have a sequence of increasing sets, and they will converge to the desired probability. And so I can use that to read the chart. Clear? So it's 2/3 minus 1/2, or it's it's really 4, 6 minus 3, 6. So it's 1/6, as some of you said. So the answer is 1/6. Good? Don't worry if you think I erased it, the answers are obviously here. You see, here I did problem B, 2/3 minus, you see it. Yeah, I rolled it out. Next challenge, guys, is probability that x is bigger than 1/2, please. Come on, I want to see more answers. So a lot of people say, well, not a lot, but 1, 2, 3, 4, 5. 5 people say, 6 people say, 7 people say, 8 people say. Going once, twice. 8 people say 3/4. So let's see if it's 3/4. Let's scroll down for the big reveal. So see, guys, I can simply say 1 minus the probability that x is less than or equal to 1/2, yes? Which is 1 minus the cumulative distribution, which is this function, at 1/2. And that's 1 minus 1/2 over 2, which is 1 minus 1/4 or 3/4. Congratulations. The answer is 3/4. And then D, I think it's the last, guys, probability that x is between 2 and 4, where it can equal to 4. I'll write it here. Go ahead, calculate this one. Okay, 2 people say something. 3. 4. 5. All right, so how can we solve this? Very simply, guys. What it is just, it's just gonna be probability at 4, less than 4, minus probability less than 2. And this is why again, because to be between 2 and 4, you must be less than or equal to 4 and not less than or equal to 2. Do you agree? It's complement. Yeah, it's complement. And so what is, when I take the complement, what happens? It's really the same as probability that x is less than or equal to 4 minus the probability of the intersection. And x less than 4 contains x less than 2. So the answer is just probability x less than 4 minus x less than 2, which is the cumulative at 4 minus the cumulative at 2, which is 1 minus 11 over 12, which is 1 over 12. What would it be? Just to change the question a little bit, guys. Yes, you can write it, of course, depends on what I say. I try to not ask questions that are too boring, but who knows, right? I would like you to justify when I say justify, but otherwise you don't have to. So tell me, please, what's the probability that x is less than or equal, or bigger than or equal to 2 and less than or equal to Or just let's make it less than 3. Good. What is this? Okay. Okay, Rodra. Come on, guys. It's simple. So Sarah says 0 minus 1 over 12. It cannot be negative. It's impossible because probability is not negative. All right, so how do we do that? See, you're getting different answers, guys. So what is the situation? The situation is we need to be less than 3 and not less than 2. Yes? Less than or equal, we have to be not less than, just less than 3. It's important. Less than 3, but not less than 2. So that's the probability that x is less than 3 minus the probability, can I skip and just say less than 2? Do you see? It's probability x less than 3 minus probability x less than 2. Everybody understands why? Because x less than 3 intersect x less than 2 is just x less than 2. Good? Now, what is this going to do, guys? How do I calculate x less than 3? I need to take something like limit as n goes to infinity of the function at 3 minus 1 over n. You see why? Because I need to creep up to 3. Minus the probability where x is, of the function. Two minus 1 over n. And what do we get? So f of 3 minus 1 over n, it's here. So it's 11 over 12. Do you see? It's always 11 over 12 as I creep in towards 3. And as I creep in towards 2, I am at 2/3. You see? So it's that minus 2/3. Here is your answer. You can simplify it if you like. But you understand the point. It's 11 over 12 minus 2/3. Good? No? So Sarah, you're bothered by it.
I think I'm not fully understanding the logic. Like, is 2/3 the value, the probability of x when x is less than 2, or is it the probability when x is, like, I'm confused why we're not also subtracting out x over 2.
Because x over 2 is the distribution below 1, but we are below 2. So it's like this. It's based on you see, what is this? Just I can interpret x less than 3 as almost like x less than or equal to 3. So where do I see in this in this outputs x less than 3? It means plug into this function 3. Plug instead of x 3. So I look at, if I plug in the x, if I plug in the x a number smaller than 3, be careful. 3, it would be 1. If I plug in 3, it would be 1. You see, I don't plug the function at 3, but as I move closer and closer to 3, I'm where? I'm in this interval. I'm below 3. I'm in here. So I plug x's that are slightly smaller than 3, and the output is constantly 11 over 12. Do you see that?
So I guess what I'm seeing is that when x is less
For
than,
example, if I plug in the number 1/2, right, into this function, I'm omitting the x. What is that asking? This is the same as asking the probability where x is less than or equal to 1/2. Okay, and then I see in this function what happened if I plug 1/2. Well, if the number I plug in is between 0 and 1, then I use this formula. So that the result is 1/2 divided by 2. The result is 1/4. Okay, this is what this function is telling me. Not because I understand why it's telling me that, but because that's what it's telling me, right? The function has been given. Good. You see what I mean, right? So this function, when you plug in a number, it will tell you the probability that your random variable will be less than or equal to that number that you selected. That's what this function is doing. And then I can use, that's all this exercise is about. In a moment, we can kind of forget about it and return to expected value discussions and then come back to it, right? I personally introduced it in this chapter only because I thought maybe in what I'll develop it would somehow figure and maybe before chapter 5, but really that's where it's going to be important. Yeah, so Roadna says the probability that x is less than 2 is 2/3. That includes probability x less than 1, which is 1/2. Right, so Roadna tries to explain that it already includes yes, but you're thinking in terms of Rhonda tries to explain in terms of what probabilities are doing. I'm just saying simply, this is the function. Plug a number, and here you can see that number, right? So plug in 2, and what would you see? If you plug into this function 2, you will see output is 11 over 12. Now the meaning of plugging into is the probability that x is less than or equal to 2. Yeah. And the formulas, they follow logically. Somebody says something, I'm sorry. Yeah.
Can I ask, is it office hours yet? Can I ask something about?
Yes, I suppose, guys, we can stop the recording and then use the time to continue into office hours. All right, I'll stop the recording. And if you want, stay with me. And if not, goodbye.